Hello everybody. So let's start the class. So we were studying the forces. We studied concurrent coplanar forces in 2D. Now let's study the equilibrium of concurrent non-coplanar forces. It's the equilibrium of a particle in space. So suppose there are three force vectors F1, F2 and F3. Which are directed along X, Y, X, Z and Y directions respectively. So if we find the resultant, then we can follow the same process what we do in 2D forces. The forces in coplanar forces, same procedure we can follow here. For non-concurrent coplanar forces, here we are applying it for concurrent coplanar forces, and even for why non-concurrent, I'll let you know later. But here at the moment, concurrent coplanar forces and then concurrent non-coplanar forces here. So we are just comparing the two, and F1, F2, F3, we just draw a vector to some scale along their respective directions, and then connect the head of the tail of the last vector to the head of the tail of the first vector to the head of the last vector, and we get the resultant. So this way we can establish or we can extend the application of concepts what we studied for concurrent coplanar forces to concurrent non-coplanar forces also. Here we do something more. In the forces, space forces, we take the projections, we work out the projections. The projections of say Fi in this space we can obtain on a plane perpendicular to the z-axis. Say in this case, so that projection is on say xy plane, and then just drop a normal from A and normal from B, the tail and head of vector Fi on this plane, and then connect this to O, so we can get the position vectors for tail and end, tail and head of these vector, projected vector. Now this thing we'll discuss later, but at the moment here just I wanted to discuss this, that we take projections also here. So here as we discussed the concurrent non-coplanar forces, we can establish their resultant as say R in this manner. Now we have to establish the equilibrium of these space forces. So here equilibrium of a point of application or particle in space coordinates, located in the space coordinates, subjected to concurrent non-coplanar forces. So for equilibrium, as we studied in coplanar force cases, that resultant vanishes. Resultant must be 0. So if resultant has to be 0, then we can write the equilibrium equation here. We can, as we discussed earlier, 3D vectors we can write as its x projection rx, I, ry, j, rz, k. And suppose n number of forces are acting at a point in the space coordinates, then for each vector we can represent as say fxi plus fxi plus fyj plus fjk, or here I have used a variable capital Xi plus capital Yj plus capital Zk, and a subscript I has been used to define the ith force vector. So summing the x components of all the forces at a particular point or a joint or at a particular particle on a particular particle, we get the Rx, the projection of the x projection of the resultant R. Similarly, sigma Yi will be the y projection of resultant, and sigma Zi will be z projection of the resultant. So here xi, yi, zi, these are actually the scalar values. These should be multiplied by the unit vectors along x, y, and z respectively to express them as vector quantities. But here, from this, we establish the equilibrium equations conditions, which is a scalar relation here. So sigma Rx is equal to sigma xi. And if this is 0, then we can say that we got one equilibrium equation of summation of forces, components of forces along x direction. And for equilibrium, for R to be 0, Rx must be 0. Similarly, we can write sigma Yi equal to 0 and sigma Zi equal to 0. So Ry, Rx, Ry, and Rz individually must be 0. Then only the Rx, R vector, the resultant vector will be 0, and the point of application of all these forces will be in equilibrium. Here we are dealing with the static forces, so the point will be at rest. So this is how we get the equilibrium equations are established, the equilibrium of concurrent non-coplanar forces, and we get in this case 3 equilibrium equations. Now some observations based on our above discussion. First observation is this: as we have established that for this point of application of resultant R, that is O, which is the resultant of F1, F2, and F3, and if the point O is to be in equilibrium, then for this sigma Fx must be 0, sigma Fy must be 0, sigma Fz must be 0. And here in this case only 3 forces are there, F1, F2, F3. So sigma Fx is F1, sigma Fy is F2, and sigma Fz is F3. So it means what? If there are 3 forces, space forces acting at a point and for the equilibrium, then all these 3 forces must be individually 0. Then only the point O will be in equilibrium. Otherwise, it will not be in equilibrium. So if 3 forces are acting, if these F1, F2, F3 are not 0, it's a trivial condition. It's of no use. No force is acting there. So if forces are acting in this manner, that one is along x, another is along y, third is along z, then the point of application will never be in equilibrium. That is one observation. So similarly, but here one thing we can say, one more comment is here, that say at a point here 3 forces are there. So if 3 forces are there and out of the 3, 2 are coplanar, this is third comment here. If all the forces are coplanar except the nth force vector, so in this case F1 and F2 are coplanar forces, so then for the point to be in equilibrium, then what Fn should be 0. This is another specific case. This happens in when we resolve the actions in plane, particular plane. These things we'll discuss in space process analysis. So this is another condition must be satisfied. So then resultant of F1 and F2 will be say OC, and but this is not applicable in this particular case. This will be applicable suppose when there are n number of vectors and all those are coplanar, except one, then nth vector must be 0. So in this case, for the equilibrium of the point, this resultant must also vanish. OC must also vanish, but which is, if it is not 0, then point O will not be equilibrium. So first condition is perfect here. Now, if two out of the four space forces are collinear, here four space forces may be there. Out of four, they may be collinear. Two may be collinear. Like there are four forces. One was OC, F1, F3, F2, and let's say F1 and F2 are collinear. Then the equilibrium of particle will exist only if the other forces like OC and OD are individually zero. Otherwise, they will not be in equilibrium. So F1 and F2 are collinear, plus their direction magnitudes must be equal and directions must be opposite to each other. So these are some observations. Based on these observations, we take the advantage of these kind of understandings later, and we can work out the space thrust forces very fast in this manner. That we'll attempt some examples that we will discuss it again. So let's do an example here. On a wall, there are 2 points B and C located from the origin expressed say at this point below the dotted line at the bottom of the wall. So B is at say 8 meter. Now here we are expressing the Z axis in the OB direction, and X axis is along. Say this is shown here, OX and OY like this. So origin of the coordinates of all the points here is O for the wall. Now B is located at 0x, 8, 12y and 8z in the z direction. Similarly, C is located at 0x, 12y and 10 minus 10z in the z direction. Now, in this wall, there are 2 points, so support points B and C. There may be hooks through which we are connecting the 2 inextensible ropes here, say at A. And at A, we want to hold a weight whose mass is 200 kg. And to hold this, we require, in this case, position, we require one additional force P should be applied, and it has been applied in the X direction. The A is located at 2 meter along y-axis and 1.2 meter along x-axis from the origin. It doesn't have z coordinate here. So there are 4 forces now. W, that is mg 200 into 9.81, and one force will be the, because this load is hanging through this rope system, so all these ropes are either flexible or taut. They may be stretched or unstressed, unstressed conditions. In unstressed conditions, so they will get subjected to tension only. This particular aspect we'll discuss later. So the force in member AC will be TAC, and that will be, if we draw the free body diagram of joint A. Joint A means what we do, we physically cut these ropes A, B, A, C, and say this rope is here cut again, through which we are applying the load, and W. So there are 4 actions will be there, will be represented by the directions of these ropes. So one is TAC will be directed along C from A to C, TAB directed along B from A to B, and T as shown. So these will be 3 forces and one W, that is 200 into G. Now we have to analyze this joint and find the tension in the chords in these inextensible members, so that we can hold these weight in position as shown at A. So this geometry is stable at rest. Load is at rest. So first what we do, first we define all these forces. So let's say define force P. So its magnitude is P is directed along x-axis, so it is Pi, and W is directed down in the downward direction here. So that is minus mgj along J. But here in this case now, one more important point before we move further. Earlier we defined the origin at the base of the wall somewhere at O, but actually when we are analyzing the joint A, then we have to shift this origin to A, from O to A, or a new local coordinate system we need to define. Suppose this is a global coordinate system which defines the entire structure and forcing system. Now we need to move from O to some local coordinate system that will also be 3D coordinate system. Pass origin must be at A. Now through A, W is downward, so minus mgj through A, P is horizontal parallel to along x-axis, so it is Pi. So W is minus 1962 J. Here I have just written Newton to express the units, but actually Newton should not be written inside this, rather it should be written outside J. So it should be 1962 J Newton force. Now to define TAC and TAV, we need to define unit vector along AC and along AB, and then magnitude multiplied by that unit vector will express the force in this particular direction, in the direction of lambda, that unit vector. So TAB is here. TAB should not have been bold-faced, rather it is a simple magnitude. So TAB into lambda AB. Lambda AB can be bold-faced, or it's better we just write an arrow above these variables. So accented by arrow. So first let me work out the lambda AB. Now for lambda AB, we know the coordinates of A, we know the coordinates of B, so we can establish the vector AB. And vector AB now from origin at A. So its x coordinate of B is minus 1.2 J, 1.2 I. The y coordinate of B with respect to origin at A is 12 meter minus 2, so it is 10 J, and the Z coordinate is 8 K. It is in the positive direction. So this is how we have established the vector AB, and length of the vector AB will be square root of 1.2 square plus 10 square plus 8 square. That comes out to be 12.862 meter. So lambda AB, the unit vector along AB, will be the vector AB divided by the length of the magnitude of this vector. So it is minus 0.0933 I plus 0.7775 J plus 0.6220 K. Now in this, simply multiply the TAB, the unknown variable here, and we get the force vector TAB, which is essentially a tensile force, and this called AB. Similarly, we establish lambda AC in the same manner. So lambda AC length is 14.193, and the vector is minus 0.084455 I plus 0.7046 J minus 0.7046 K. So then TAC can be written simply by multiplying, because TAC is unknown. So multiply this magnitude TAC as an unknown variable. So this way we get vector TAC. Now equilibrium. We know the direction of W is downward. Direction of P is towards right, positive. Here when we write the equilibrium equation of forces at joint A, the vector equation here, we always, because we express the directions here as minus mgj. If you don't express here minus mgj, but in vector form when we write, it should be written always with sign, proper sign. So then when we are writing the equilibrium equation at joint A, so it is sigma f equal to 0. So simply it is the summation. We should write it in summation form. So it is TAB plus TAC plus P plus W is equal to 0. Sum of all the forces at this joint must be equal to 0. So now we can substitute here TAB we have derived, obtained, and TAC we have obtained, P we have obtained, W we have obtained. Now here you can rearrange the terms and club the values, multipliers, scalar multipliers of I, J and K. So we get the equilibrium equation at joint A as minus 0.09330 TAB minus 0.08455 TAC plus P I plus 0.7775 TAB plus 0.7046 TAC minus 1962 J plus 0.6220 TAB minus 0.7046 TAC K equal to 0. So this is the equilibrium equation at joint A. Now from this we can arrive at the three equilibrium equations in a scalar form: sigma fx equal to 0, sigma fy equal to 0, sigma fz equal to 0. It should be sigma, and here it should be subscript must be x. Take a writing mistake here. So we get three equilibrium equations: one along I, another along J, third along K, or along x, y, z axes respectively. So three equilibrium equations. There are three unknowns: TAB, TAC, and P. So we solve them. Three simultaneous equations. You can follow any rule, matrix approach or Gaussian elimination approach, or whatever you want. use your choice, and then we can solve this force. P, it comes out to be 235 Newton, 1442 Newton TAB, and 1238 Newton TAC. Results are positive. In the chords, flexible chords, always the forces will be tensile, so positive. Now let me define some actions here. There are external actions and internal actions. So external actions are those actions which are applied. Internal actions are those actions which induce because of the application of the actions. So here you see there are two external actions. One is F, another is W. So W is the external action and F is the pull applied by these people. So this is an external action. Internal action here is one, R1 and R2. And if we if we draw the free body diagram here, then rope will be subjected to some internal force. Induced force will be in the rope. If we draw the free body diagram of this particular truck, then we eliminate the people who are pulling it. We simply write it as an internal action. So then F will become an internal action on the rope. So here we see only the rope. And ropes, because the external action gets transmitted from the rope to another point because of the development of internal forces, because of these induced forces. So F becomes internal, W is external, and R1 and R2 are the reactionary forces. These are also the induced forces, so they are called internal actions. Now let's discuss the principle of transmissibility for establishing the equivalent forces. So here you see this truck is getting pulled by force F using the rope by people standing here. Or if say these people come behind and they start pushing it in the same line of action, then whatever speed this particular truck say it is set in motion with uniform motion, then along the line of action of force F we apply a push here. So F dash and F will be equal. Now what we have done here, we have transmitted the point of application of F from the front of the truck to the back of this truck in the form of F dash. But here, if line of action of both these are same, then F will be equal to F dash if the condition of motion we don't want to change of this truck. Because weight is same, reactions are same. So here in this case, this is the situation. So actually, here, suppose the point of application is 2D plane. Here in this body is a 2D structure, and along the line of action here, it may be 3D also. So if the line of action of the force is maintained, the point of application we can shift along the line of action, and if we do so, then the effect produced by this force on the body will not change. That is one important thing. This is known as the principle of transmissibility of forces. This comes out to be very handy approach to analyze the structures. If some problems we'll do here, we'll discuss its application, and then you will use extensively in structure analysis. Let's come back again to the vector mechanics, mathematics of the vectors. So here you see there are two vectors A and B. And if we take the dot product of A and B, then A dot B is equal to AB cos theta. And from this relation, if you want to find out the inclination, the angle between the two vectors, then simply what we do, A dot B divided by magnitude of, product of A and B is equal to cos theta. So cos inverse of this value will give us the angle between the two vectors. Now here A dot B and B dot A is commutative here. So we can write either A dot B or B dot A. And it is distributive also, that A dot B plus C is equal to A dot B plus A dot C, or in this case it is this. So A dot B plus A dot C, this property is the distributive property. And usually we express I, J, K as unit vectors along x, y, and z axes respectively. So these vectors can be represented in the form of their x, y, and z component. So it will be axi plus ayj plus azk dot bxi plus byj plus bzk. And we know here the property that I dot I is 0. If the angle theta is 0, means cos theta is 1. So it is I dot I will be unity and I dot j. You have studied a lot this thing. So I dot j is 0 because cos pi by 2 is 0. So then this product simply will be the ax bx plus ay by plus az bz. Now vector product here. So this is also sometimes known as dot product as the scalar product because it produces scalar results. And another product we call as vector product, that is cross product. So A cross B is equal to C. Now A cross B here is written in this fashion. So suppose vector A is along say any axis, and then we rotate. A cross B means we rotate from A to B, and the resultant vector gets produced in the direction of palm. So we follow the right hand palm rule. Finger curling tells us the direction of rotation of these vectors. Getting the product of this vector from A to B, then positive vector C, the product will be along the direction C. And this L is a negative vector. If we do the product from B to A, we'll get the negative vector. So A cross B is not equal to B cross A, rather it is minus B cross A. Now A cross B here we can write in the same manner as we did in the dot product. So AXI plus AYJ plus AZK cross BXI plus BYJ plus BZK. And it's very handy if we attempt it using a indeterminate form and get the determinant of these coefficients, multipliers, scalar multipliers. So in the first row we write IJK, and so it will become a 3 by 3 matrix, and then its determinant we write. So AX, AY, AZ is the first vector, and BX, BY, BZ is the second vector. Then get the determinant of this, and you get the C vector C, that AY, BZ minus AZ, BY, I plus AZ, BX minus AX, BZ, J plus AX, BY minus AY, BX, K. Now, as we know, in the cross products, we can follow this rule. Draw this circle having three locations of I, J, and K. If we move anti-clockwise here, so right hand palm, we curl it in anti-clockwise, then the thumb points to the positive vector K, and we are moving from I to J. So I to J gives K, K to I, K cross I gives J, and if we reverse the direction of computation, then K to J gives minus I, and I to K gives minus J, so that you know. Here one more thing, if angle is 0, so I cross I is 0, J cross J is 0, K cross K is 0, just repetition, everybody knows this, so you know all these things. Here it's a mixed triple product, one very important relation, we'll use it somewhere. So let's discuss this. It's a rule to express this triple product. So we write in this circular arrow and draw the arrow in anti-clockwise fashion. Say there are three vectors, so A, B, C, and then again repeat A and B. So this in this particular order, we write these three vectors, and then say we want to find out A cross B dot C, then A cross B dot C will be equal to A dot B cross C here. And so actually, what do we do as a rule to remember? A, B, C, we write in the same order, A, B, C, and then A cross B dot C and A dot B cross C. So simply swap cross and dot, and we get the equal vector, equal triple product. Okay, so that will be a scalar quantity actually in this case, because there is a dot product. So A cross B is a vector, dot C is a vector. So A dot C will be that some vector from here, and dot that will be a scalar quantity. Now, one interesting thing is this, that if we move in this order and we place a BCA, B cross C dot A, then B dot C cross A, this is equal to, and this result is equal to the previous result what we have worked out. So in this manner, we get 6 relations of equality in this order. So B cross C dot A is B dot C cross A, C cross A dot B is C dot A cross B. So simply swap the dot and cross, and you get the result. Any of this form can be used in the analysis. Now let's work out the moment of a force. Now moment of a force about an axis we call as torque. later you will clearly understand, because all the three moments are about an axis, but axis means longitudinal axis. So if it is about the longitudinal axis, it is called torque. If it is about cross-sectional axis, we define it as bending moment. This particular thing we'll discuss again later somewhere when we'll deal with the beam. And in that case, you will have here it is a circular cross section. So the cross sectional axes are say o perpendicular to the plane of this, perpendicular to the axis, a plane perpendicular to axis O. Will get that on that plane there will be two cross sectional axes. So moment about those axes we define as the bending moment, because that causes bending. But this moment causes twisting, so we call it torque. Now moment about O, how to get that? This is what we have to study here in this case. So suppose there is a force vector we are applying through this spanner on and trying to open this nut. We are trying to open this nut, say. So here F is multiplied as shown in the figure to the using this hand, and then perpendicular distance from the axis of O axis, distance is d. So F into d will be the moment. Now F into d is the moment. Now F here you can take a scalar value, d is scalar value, and then its direction will be positive. If our right hand palm curling tells us the moment direction, rotation direction, then the thumb points towards the positive direction of this vector, that is the moment vector F into d. So MO will be positive in this direction. So it is shown in this book, Beer and Johnston. They have shown it using this arrow to represent the rotation and this arrow to represent the magnitude. But actually it is not convenient when we draw it and write it manually. Then if I prefer, we prefer, some people prefer using double arrowheads here. So instead of using single arrowhead here, we use for forces, and double arrowheads to represent, differentiated from force, we use double arrowhead to represent the moment. There is another approach, and that is very consistent and very strong approach to understand the moment, that is R cross F. Moment about O in same problem. Let's see here, suppose force is acting here at a position vector R from the point of application about which we want to work out the moment, point A. So position vector is R and force vector is F. Then deviation of F with respect to R is say alpha. Then what we will get here, if this angle is alpha, then perpendicular distance from this, so this angle will be alpha, the opposite angle will be alpha, this will be pi by 2 minus alpha. So the projection of R pi R on D on a normal from A on line of action of F will be R cos pi by 2 minus alpha or sine alpha. Or otherwise what we can do, we can find out F sine alpha. So F sine alpha will be a perpendicular component of this. The longitudinal component F cos alpha will pass through O, so that is along the position vector, so it will not cause any moment about O or about A, but the normal component, normal to R, will cause a moment along O, that is at O perpendicular to this plane of these two vectors. So vector F and vector R are there, and they are coplanar, and the O moment vector at A will be perpendicular to this plane. So here FR sine alpha is the moment about axis OO, and this is nothing but R cross F. So this is a very important formulation. This gives us the correct sign of the force moment vector here. So I always prefer and I always suggest that you should use this form rather than this. But sometimes in easier problems, it is more convenient to get the moment directly using F and D approach. But their directions also we must visualize, we must try to understand. In this case, direction will come automatically if you correctly write vector R and vector F. And here, to represent the sense of the moment, the direction of the moment will follow the right hand finger curling rule, or it is an extension of right hand screw rule. Now here, one very interesting application of principle of transmissibility, transmissibility law, transmissibility of forces. So let's see this example here. Suppose point O is there, about which you want to find out the moment of force F. Now F is line of action is given. Point of application may be say at position vector R1 or at R2 or at R3. What will happen in this case? So as we have studied that if suppose force F is acting at the position vector R1, then the moment about O will be in the anti-clockwise direction as shown, and it will be R1 cross F. Now, if we shift the force F to another point of application of the same line of action, this moment will be equal to R2 cross F. And third position here again we shift, it will be R3 cross F. But in this case, one interesting thing you see for all the three position vectors, the normal distance, perpendicular distance from O to 4, this force will always be equal, that D will be equal. So moment remains same. So even if there is a force point of application changes, we apply the law of transmissibility of forces, it is not going to alter the moment produced by this force on the body. So that's why this transmissibility is applicable. Now there is another very important principle, that is Varignon's theorem, that is principle of moment. So in this case, suppose we have a force vector F drawn using blue line, and its position vector is R from O, and R and F both are in the same plane. Then the moment produced by F about O perpendicular to the plane of F and R will be R cross F. And as we know vector summation relation, that F is F1 plus F2, so R cross F1 plus F2. So then here what are F1 and F2? F1 or F2 are the components of this vector F, which have been obtained by using the parallelogram law. So we get the component of F along a given directions, So F1 and F2 are their components. So if the moment produced by F is R cross F, this is equal to R cross F1 plus F2, or we can open this bracket actually. So produced by individual components F1 R cross F1 plus R cross F2 is the total moment R cross F. So this theorem, this principle is known as Varignon's theorem. So this is also a very important result we get. It has got a lot of applications. Those things we'll discuss later here. So we'll apply law of transmissibility, principle of transmissibility, principle of moments, that is Varignon's theorem here in the analysis. Now let's get the rectangular components of a moment. Now we got the moment about O, that is R cross F, because of a given force. A given force we can express in three vector components along x, y, and z axes respectively. So it will be fxi plus fyj plus fzk. So suppose the point of application A is at xyz coordinate from origin O, and then A has the position vector R. Then here force we can write in this fashion, fxi plus fyj plus fzk, and R we can write as xi plus yj plus zk. Then M also can be written in the same form, that mxi plus myj plus mzk, because M is a vector quantity, Mo is a vector quantity. So it can have a component along x, along y, and along z too. So we can, to get this moment again, we write in the determinant form. So I, j, k, x, y, z are the coordinates of the point O, which are representing this position vector associated with I, j, and k. Then similarly fx and fy in the third row, and we get the moments from this. The determinant of this relation gives us the moment component. So mx will be yfz minus zfy, my will be zfx minus xfz, and mz will be xfy minus yfx. So these are mx, my, and mz components for this condition, for this situation. Now here sometimes you may be knowing the coordinates of the point, and point about which we want to take the moment may not be the origin point, the global origin. So it may be some other point B, and whose coordinates are like xb, yb, zb, and coordinates of here xa, ya, xa, ya, and za. Then in that case, projection of the position vector RAB. So whenever we want to find out the moment of a force about a point, then the position vector has to be written in the reverse direction. You see, A is the point of application. So from the point B to A, we should write the position vector from B to A. So that is RAB. So position vector representing the position of A with respect to B. This is what we mean. So it's a not from A to B, rather it is from B to A. This is very important point here to note when we use this relation. So it is RAB. Here actually it is position vector of A with respect to B cross F, and position vector of B with respect to A is B. Position vector of A with respect to B is the with respect to new origin. So we can find out the x, y, z intercepts are the projections of this. So we can write this as xa minus xb I plus ya minus yb j plus za minus zb k, or we can write in another manner that if you write this RAB, so it would be RB, and we can join the position vector of A. So RA minus RB will be RAB, right? So RA minus RB, you know the position vector of A and you know the position vector of B. So RA minus RB is RAB vector. So in this case, then we can write again in the determinant form. F is in fx, fxi, fyj, fzk. So here we write in the determinant form the first row ijk, second row xa minus xb, ya minus yb, zd minus zb, third row fx, fy, fz, and we get the determinant of this relation that will express the moment about point B. So we will get the rectangular components of the moment about point B. Now another very important exercise, this we require in space trusses to get the moments of forces about an axis. So this is also a very important exercise. Let's discuss this. Now there is a force vector F acting at some point, say A, whose position vector is expressed by R. So moment about O passing through the origin is R cross F. Now here our task is to find out the moment of this force about an axis OL. About an axis OL, which is represented by a unit vector lambda. So we need to know the lambda, and then the moment of force about this axis will be in the direction which is represented by lambda. So in this case, what do we do? A very simple exercise we attempt here. We try to find MOL by taking this dot product, because we know the unit vector along OL, that is OC, that is lambda, and then here lambda dot MO will give us the moment vector, or that is in fact the projection of this vector on a line. So to get the projection of a vector on a line, we use dot product. But this will give us a scalar value, because dot product is a scalar value. So it gives us the scalar value of the moment, and direction will be obtained from the, or it will get directed, and it will be directed along lambda. This is one important thing. So lambda dot MO is lambda dot R cross F. It is a triple product here. So we need to know R, we need to know F, and then mixed triple product, and we need to know lambda, and we get moment of this force about an axis OL. So we know mx, my, mz. Here we substitute here in terms of R cross F, and then take the dot product, and we get the moment about this and about this axis. Now one important exercise here, when we say moment about an axis, then this moment should remain invariant if we change the point of calculation, right? Now here we calculated the moment about, say, this point O. If we shift the point O to some other point, say C, or some other point D, or any other point on this line OL, then this moment should remain invariant. That is one important requirement for this result, that moment of a force about an axis must be same about that axis. Let's prove that here. So as suppose we have a point B about which we want to work out the moment of force F which is acting at point A. So in this case, position vector of A with respect to B is RAB. So MB will be RAB cross F, and then suppose we have a line BL line, and this unit vector is directed along lambda as shown. So then the projection of MB on line BL will be lambda dot MB. So lambda dot MB is lambda dot RAB cross F. Now RAB as we defined is the RA minus RB, where R is the position vector of A and RB is the position vector of B. So RA minus RB is RAB. Now here let's shift the point of calculation of this moment to C. Now when we work out the moment of F about C, it would be say RAC. So in this case, here it would be RAC. So RA minus RC in cross F into lambda. So lambda dot RA minus RC cross F will be the moment about line BL. Now this relation we can write in this fashion. What we do, as we have studied in Barry-Cannon's theorem, that we can open this class product, open these brackets of this class product, and we'll get the same result. So here we can write it like this: lambda dot RA minus RB cross F plus lambda dot RB minus RC cross F. Now you see RB minus RC dot lambda dot RB minus RC, because RB minus RC here, RB minus RC is this line BC, so which is collinear with lambda. So the dot product of the collinear lines will be here. This will be 0. Will it be? I dot I, no, it is not 0, but rather it will be perpendicular to this. So when we do the cross product of this, we get a vector perpendicular to this. So the normal vector lambda dot this perpendicular vector will be 0. So this entire product will be 0. Triple product will be 0. So then we can say this comes out to be again here is RA minus RB dot cross F. Here lambda dot RA minus RB cross F value, which is MBL. So MBL is same as we obtained here. So it means if we shift the point of calculation of moment about an axis anywhere on that axis, on that line, then moment remains invariant. That is one important point here. Let's do the calculation of these moments. Some simple exercises. These are vector, expressing the vectors and then finding the point of location of the point of application and getting the moment of these applied force. So in one example, say we have a force here. Written like this. So here force 600 Newton is acting at point A. Now A has a coordinate in y direction 4 meter and in x direction 2 meter. So point of application of 600 Newton is at A and it is directed at 40 degree as shown in this figure. So we have to find out the moment of this force about O. So for this, one concept is just find the perpendicular distance D from the point of about which we want to find out the moment. So we just drop a normal from O on the line of action of force F, which is D here. Now we have to find, our task is to find D. Now this D can be worked out as, so first we need to express these angles. So this angle is 40 degree. If this angle is 40 degree, then if this angle is 40 degree, then opposite angle here will be 40 degree. This here, and so if we draw a normal here, we can drop a normal from here. So in the direction of line this, so this would be 60 degree, and this 50 degree, and this again this angle will be 40 degree. Or because it is two parallel lines are, if we drop a normal on D here also from this point, then two parallel lines are there. So this angle is 40 and this angle will also be 40. Now using this we can find out the distance D. So 4 cos 40. If now this is 40 here, this will be 50, and in this right angle triangle this will be 40 again. So this would be 4 cos 40, that is part 1 of this length. And it would be 2 sine 40 in this case, because 2 cos 40 will be this distance. So 2 sine 40 is this. So 2 sine 40 plus 4 cos 40 will be D, that is 4.35 meter. So 600 into 4.35 is 2610 Newton meter. That is the moment about O. Now this can be done in so many ways, like all those approaches we discuss here. So another approach, simplest approach is what? Just resolve this force along horizontal direction parallel to x-axis, along vertical direction parallel to y-axis, and get the moment. Here, so it would be 600 sine 40 vertically downward component, and 600 cos 40 horizontal towards right component. So 600 cos 40 into 4 plus 600 sine 40 into 2 will be the moment 2610. Okay. So fx component is 460 and fx component is 460 and fy component is 386. This would be fy. I think this is a typing mistake here. There's another approach that is also a very interesting geometry approach. What we can do, we can extend the line of action of f from A to meet a vertical from O at some point here. Then what we see here, say this distance is D1 from O. So if we take the component of F along horizontal and along vertical, so vertical component will pass through O, will not cause any moment. Then it would be horizontal component only will cause the moment, that multiplied by D1. So D1 here is actually this. So this distance is 4 and this angle is 40 degrees. So this opposite angle is 40 degrees. So this distance will be 2 tan 40. So 2 tan 40 plus 4 would be 5.68. So 460, that is fx component about this from shifted to this point. That is the application of law of transmissibility of forces. So we are shifting this force to this point, and then 460 into 5.68 is 2610. Another approach, shift this point F to this point. Now in this case, horizontal component will pass through this point O, will not cause any moment. The vertically downward component will cause the moment. So that is 386 into this distance D2. And D2 we can work out as the 2 meter plus this distance is 4 meters. So this angle is 40. So this angle is alternate interior angle. So this is horizontal will be cot 40. So 4 cot 40 plus 2 is 6.77 meter multiplied by 386, 2610 Newton meter. Another approach is vector approach. So in structure analysis, in mechanics, everywhere, my suggestion is you must apply the geometry extensively. It helps a lot, it simplifies your work, and you understand the things properly. Vector approach are also very good, mathematical approach. So we know the position vector R of O with respect to O, that is twice I x coordinate, 4j y coordinate, so twice I 4j cross 600. Now its direction cosine, now we have to find out. So the direction cosine here is cos 40, and in this case its vertical axis is upward, so this component will be negative here, that is cos pi by 2 minus 40, so it is minus sine 40j. So from this we take the cross product here, R cross F, we get one very important result. Here see in the above results we did not mention the sign of the moment, in which direction it will get applied, but here it will get applied in the negative direction. So if this is the xy plane, if x-axis and y-axis, in this case according to the right hand screw rule, perpendicular z-axis will be here in this direction. So if you place your eye somewhere here, you will see the head of the arrow representing the z-axis. So this vector is not getting directed along positive z-axis, rather it is getting directed along negative z-axis. So at this point we will see the tail of this vector. So to represent, actually here it is not drawn, but we draw a circle, and inside this circle we draw a cross. So that represents the tail of the vector. When we want to draw a vector in 2D, and if it is head, then we draw a circle, and inside at the center of this circle we draw a dot that represents head of the vector. So in this case it will be tail of the vector seen from this side in this 2D plane. So this is how it is why it is very important, R cross F. If you properly represent these vectors R and F, you will get moment vector with proper sign also. Now time is over. Let's stop here. We'll discuss the moments of couple, and then lot of examples in couples, and then here equivalent couple, and then reduction of forces into resultant and moment. These are the things we have to study in this topic, in this chapter. So let's stop here. So please write something in the chat box.